Hello everyone. So in this session we'll go through few of the important problems. So before going to those problems we'll understand about time complexity. So time complexity helps us to identify the amount of time taken to run a particular code based on the input size. So when you have an array and you are trying to pull any of the index element, so this takes O of one time. And when you have an array of n elements and you are trying to traverse the entire array and perform any operation, then it takes O of n time. O of n basically means the worst time case. And in case you have two loops with each having a size of n, so for I value of 1, the inner loop runs n times. For I value of 2 it will run n times. So for I value of n it will run n times. So this will be O of n square. O of n cross m is same, just that the inner loop will run m times. Now log n time is basically when you have an input array and every time you are trying to divide the array and such only in one half. So at each interval, at for each operation, I mean for each iteration you are trying to reduce the size of the array by half. Then it means that it will take log n time to perform this code. So binary search algorithm also divide and conquer. So basically it will divide the array into half and run uh, search for the element. So every time it will divide. So this time complexity will take log n time. You should note that log n time is better than O of n. Now n log n, any of the sorting algorithm, the best sorting algorithm such as quick sort and heap sort will take n log n time. Also heapifying will take that much time. And coming to c power n, so basically we have our operation time complexity as 2 power n. That happens when for each value of n, if you have a tree, for each level the number of child increases by 2 for each parent. Then so every time when you go down to the tree, traverse the tree downward, for each node the tree size increases with each having two child. So this will be 2 power n. Okay, so this was about the time complexity. Now we will go through few of the problems. So first, coming to the problem of finding the peak element. So given an array you have to find what is the peak element. So a peak element is an element that is greater than its uh, left neighbor and the right neighbor. So over here in this problem we can see that 8 is greater than 7 and 8 is greater than 5. So this is the peak element. So we need to return the index of the peak element. So here the index of 8 is 7. So how do you find? So this is not a sorted array. So the simple brute force approach is you are going to traverse entire array, and for each uh, value of I you will compare its left and right value and check whether it is a peak or not. So this will take a time complexity of O of n. And what can be a better approach than O of n? So if we look at the graph, we know that O of n is here, and better approach can be O of square root of n or O of log n. O of log n means every time we have to divide the array by half. So if we want to divide the array by half, what we can do is, uh, so let us assume like if we plot this all the array element in a graph, we know that there will be one peak element or there can be two peak, but we want to return any one. So what we will do is we will take the zeroth index as low and the highest index of the last element as high, and we will find a midpoint. So low plus high divided by 2. For example, mid comes here. Now we'll compare the mid value with mid minus 1. If a of mid is greater than array of mid is greater than a of mid minus 1, it means that we might have an peak this side Why? Because for example, if this here we are having the mid, so if a of mid is greater than a of mid minus 1, then it means that uh, either we might have a greater number towards its right. If we are having not having, then we'll have a lesser element on this side. If this is less, then this will become the peak. If this is not less but it is more, so again same approach will go. We might have a greater element here or a smaller element. If we have a small, then this will be the peak, or else it will go like this until the last element will be the peak. Okay, so this way, for example, if it comes here, mid comes here, we check with a of mid is greater than a of mid minus 1. No, a of mid is not greater than a of mid minus 1. Then we can assume that mid is present in this side. So we will again run this particular search for low to mid minus 1. Okay, so this is the approach that we are following. So this is a brute force approach how we are implementing. We are just checking whether it is a of array of I is greater than its left and greater than its right. So this will take O of n time. So coming to the our approach which we discussed. So in this method, find peak element, initially we check if the size of the array is only 1, then the 0th index will be the peak element. If not, then we check whether the 0th index is a peak. So for if 0th index is peaks, we just need to check its right neighbor. If the last element is peak, we just need to check its left neighbor. If nothing satisfies, now we will look into the middle of the array. So for that, first we'll set the low to 1 and then high to n minus 2. Then we will loop until low is less than or equal to high. So we'll find the mid value. Then if a of uh, first we'll check whether mid itself is a peak or not. So mid a of array of mid is greater than its left and array of mid is greater than its right. Then we'll return mid, the index. If not, then we'll check array of mid with array of mid minus 1. If array of mid is greater than array of mid minus 1, then we can assume that there is a peak in the right side. So we will change the low from 0 something like that to mid plus 1. Else we will change the high to mid minus 1. And finally, if there is no peak found, we will return a minus 1. Okay, so this is how it takes. Now let's look into the next problem, that is to find minimum or maximum element of an array. So you are given an array, you want to find what is the minimum element and what is the maximum element. So how do you find that? Simple solution, do a sort. So if you sort, the lowest element will be in the 0th index and the highest element will be in the minus 1 index. So this sorting, by default it will take n log n time and time complex and space complexity of O of n. Now again there is some simple other way to do if of in order to do a reverse of a element, reverse of an array, you can basically perform the sorted operation on the list with reverse is equal to true. The other approach is you can set you can have two counter variables max and min and set the initial value as the max and min, then loop through all the integers, and if if ith index value is greater than the max, then that will be the max. If ith index value is less than the min, then that will be the min. Okay, so this is how. Now the third problem is the bubble sort problem. How to do a bubble sort? So bubble sort takes O of n square time complexity. It will have a two loop. So basically what we will do, we will first run I in the range of 0 to n, and initially we will have a variable swap which is set to false. If internally we will try to set it to, if there is any interchange happening in between, we'll change it to true. If in the first iteration for I is equal to 0, if there is no swap happening, then it means that this array is already sorted. Okay, now for I value, for each I value, we will run the j from z index 0 to n minus I minus 1. That is because for each iteration we'll have the greatest element placed in its correct position. So now we'll compare a of j and then j plus 1. If a of j is greater than a of j plus 1, we'll swap. This will go till j is till second last element. Finally, after all the swapping takes place, we'll return the array. Okay, so this is how the bubble sort takes place. How to reverse an array? So reverse an array, you will have an array. You will have the low index 0 and high index index is n minus 1, while n start is less than n. You just swap the start and end value. Okay, this will take O of n time. Now the fifth problem, that is to find the kth largest element or kth smallest element. Now you are given an array, you have asked to find kth largest element, that is k value can be some anything like second largest or third largest. So how do you find? So if we can't if we are given a problem of finding the second largest or third largest, it is easy. We can use some counters and do it by looping it into while in O of n time. But kth largest and big thing we can't do only with counter. Other approaches we can use sorting, do a sort in n log n time, and find the kth index, ARR of kth index. Again, this is if n log n is kind complexity, can we do better than n log n? So there is another approach is using heap. So what is heap? Let's look. So before going into heap, let us look how a binary tree is arranged. So basically, if we have an array, so we'll have a parent, child like this. How do we write it into an array form? To parse, to write an array in a array form, we can just go from left to right and write it into an array. So here, for example, B, C, then D, E, F, G like this. Here A, B, C, D, E. In this case, A, B, C. Again, for B, there is no child, so we give left and right as 0, left and right child is 0, and D, E. So this is how it is placed. What is a full binary tree? A full binary tree is a tree where where every node has 0 child or no child. A complete binary tree is a tree when a tree is represented into array form, there is no missing values. So if we look here, when we will try to convert this into array, we'll have a basic, it will end till here. This value will be not included, so there is no missing value. This is all, there is no missing value, even though there is no one more child here, but it ends here. But if you look here, A, B, C, this child is not there, so there will be a gap in the array, and then here, and then one more gap. This gap is fine. So but this gap is forming, so this because of that, this is not a complete binary tree. Now coming to this is fine, this is fine. Here we have 3 missing, so this is also not a complete binary tree. So this is how a heap is a complete. So now coming to what is a heap. So we have a min heap and max heap. Min heap is a complete binary tree where the smallest element where parents are the smaller than their child. Max heap are the complete binary tree where the parent are greater than their child. Now let's take an example here. So in min heap we can see that 2 is smaller than its child. 5 is parent of 9 and 16, both are greater than it. Same way in max heap the parent will be greater than the child. Okay. Now inserting a new element in a max heap, for example 60, we already have a max heap, and now we are going to insert a new element 60. So in case, what we'll do, we'll add it into the last possible value. Wherever we can add it to make a complete binary tree, we'll add it here, and then we'll compare it with its parent. Since it's a max heap, the parent should be greater, so 15 will come here, down, 60 will come here. Then we'll again compare 60 with 30. Then 30 is smaller, so 30 will come here, 60 will go here. Then 60 will compare with 50. 50 is less, so 50 will come here, 60 will go there. So finally we'll have this structure. Okay. Then building a max heap. For example, we are given a set of elements and we want to build a max heap. So first 40 came, then 3 came, then 23 came. So we are building a complete binary tree. Then next 23 came, then 42 came. For the 42 will come here, then 42 will be compared with 3. 3 is less, so 3 will come here, 42 will come here, 42 will be compared with 40, 40 will come here, 42 will go. So this will be formed. So likewise we'll form the build the heap. Now how to delete an element. So we have a max heap. Now a deletion will always take place at the root. Now we'll delete the root, we'll place the possible last element to here to maintain a complete binary tree. Then 16 will be placed here. Since it is a max heap, we will compare it with its child. So 30 is greater than 16, 16 will come here, 30 will go here, and then 16 is greater than 15, so it will be fine. What is heapify? Heapify is the process of converting a binary tree to a heap data structure. So certain operations such as insertion in a heap takes log n time, deletion takes log n time, searching will take O of n time, heapify takes O of n time, sorting takes n log n time. Now you have given an heap, how to you have a binary tree, how do you convert into heap? How do you perform heapify? So go from bottom to up, from right to left. Assume this until here, only assume till 18 and below 18. This is a tree. Is it correct? Yeah, correct. So every fruit tree node, leaf node is correct. If we come here, this is 15 and we will look only this node and below its child nodes. We will compare with 25. Since 25 is greater and it is max heap, we'll pass 25 here, 15 will come here. It will be fixed. 20 is greater than this. 40 should come here, 20 will come here, then 40 will come here. We'll have 25 here. 40, 25, then 40 will come here. 10 will go here. 40 will, yeah, 40 will go here. 40 goes here and 20 goes here, 10 comes here, then 10 is less, so 40 sorry, I think I missed something. So basically it was like this. So 25 came here, then we are comparing 40 with 20, 20 goes here, 20 comes down, then 10 will come here, then it will be replaced with 20, like that. I mean, even 12 could have been replaced, but if we replace by 12, what will happen? 12 is less than 20, so only 20 can go. Okay. Now how to use heapify in Python. So heapify, you can do it, heap operation can be done with the help of heapq package. Heapq.heapify of a list will convert into a min heap by default. So this is a list. When you do heapify on it, it is converted into a min heap. Now inserting into a heap, you can do heapq dot first we are converted to heapify, then heapq dot heap push. You can pass the heap name and the element to be pushed. Again, pop will be same. You need to just mention heapq dot heap pop and the pop element name. I mean the heap name. Now, so we looked into what is the problem that we were trying to solve was find the kth largest or smallest element. So we know that we could have done it using sorting in n log n time, but in order better than that, we try to use heap. So to solve this using heap, what we are doing is first we'll convert the list into heap using heapify. Heapq.heapify of the list converts into heap. Now, since it's a min heap, the smallest element will be in the root. If we pop now, since we need to find the kth smallest element, we will pop first three elements. So for if we pop any of the element, the next smallest element will come to the root. So we popped it three times. Final time when we pop, we'll get the smallest element. Okay, so this is how done. Now the time complexity here is n plus k log n. That is because heapy will take n of n time. We are popping k times, and for each pop after that, to rebalance the heap, it takes log n time. Okay. Now this was for kth smallest element. For kth largest element, what we'll do first, we'll multiply -1 with to each of the element, because heapify, when we do heapify, the smallest element will go to the root. Now if we multiply by a negative number, the largest element in this array will go to the top because it will become negative. First we'll multiply, we'll use list comprehension to make it negative, then we'll do heapify, then we will pop the first k -1 element, final element when we are popping we'll multiply it with -1 to get the kth largest element. So this is how we do it using heap. It takes n plus k log n time. Now the other approach is to use quicksort. Now what is, so before using quicksort, so for this we should understand how quicksort takes place. So for example, when you have an array, first you need to select a pivot element. Pivot is basically mostly selected as the last element, the element which is in the high position. And then we have a two counter pointer variables. One is I and j. J points to the low and I points to low -1. Then we will iterate j from low to high. If a of array of j is less than or equal to pivot, we will increment I with 1 and replace array of I and array of j values. So if we do perform this operation until j reaches the ith element, until the high, once it reaches high, we will replace array of I plus 1. We will replace array of I plus 1 with pivot and array of I with array of I plus 1. By doing this operation, what will happen? The pivot which is selected phi will be placed in the correct place. So even in the left side and right side is not properly sorted, but the position of phi is correct. It is placed in its correct place. Now again we would have to do the same operation, quicksort operation for the left side and the right side. Okay, so let's look into the code. So initially we will pass the array, and low has the 0th index, high has the n-1 index. Until low is less than high, we will first call the partition for the array and low of high. We'll get the index of the pivot. Then we'll again pass the array with the low as low and high as the pivot element -1, index of pivot -1. And again quicksort for the right hand side is pivot +1 comma high. Okay, so this will keep on until the entire array is sorted. So let's look into what is partition doing. So partition is setting the high element as a pivot, setting I counter as low -1, and j starts from low to high. If array of j is less than or equal to pivot, we will increment I and swap a array of I and array of j. Finally, once this iteration complete, j reaches the high, we will swap array of I plus 1 with array of I. Okay, so this is how quicksort takes place. Quicksort happens in n log n time. Now how can we use this algorithm to find the kth largest or kth smallest element? What we can do, for example, we have this particular array and we took 4 as a pivot. We placed 4 in the correct order, so 4 is placed in the third index, and we want to find second largest element. Second largest element, for example, in this case, 1 2 3 4 5 6. There are 6 elements, so 6 minus 2, length is 6. You want to find the kth index, second largest index. 6 minus 2 is 4. 0 1 2 3 4. You are going to find the element in the fourth index. You know that pivot index of pivot is 3, and index of and index of pivot is 3, and you're looking for an element which might have an index of 4. So your element is present in the right side. So now, based on the index of pivot, you found that your element is present in the right side. Now you will call the again this particular pivot quicksort operation for the right side until you find you find that you land in the pivot. So let's look into the code. So initially you call the array, you pass the array with the kth index, you find length minus k to find the largest element, and you are calling. So here we have the definition for quick select. Again, this is nothing but the partition operation that takes place. And quick select, first you call for 0, then length, the last with the high value, that is length of I minus 1 for the last element. Then it will call this method. Here this operation will take place and identify the index of pivot. Now, based on the pivot index, you're comparing with the kth index. If pivot is less than index is less than kth index, then it means that your element is present in the kth largest element is present in the right side. So you will call for pivot plus 1 comma high. If it is your pivot is greater than the position where you are looking, then you will call for low comma pivot plus 1, sorry, minus 1. So this operation will take place until you land in the pivot itself. Your pivot itself is in that kth position, and finally you will return ARR of pivot index. Okay, so these were the few problems that we solved. We'll look into other problems in the next session.